before starting the fundamentals of solid state physics, I would like to tell you something about material technology. That is our department, material technology. You can see some pictures. Well, our aim is to produce such materials actually. So those are excellent high technological materials. And okay, before all these things, I would like to tell you something about material. Now our department is materials technology. So under that department, so you are planning to listen to my lecture. Now, so first one is going to be fundamentals of materials technology. So what is a material? What is a material? If something has a mass and volume, then you call it a material. If it has a mass, right, and volume, then you call it a material. So your pen, there is a mass for that and there is a volume for that, so that is a material. If you take a piece of stone, so that has a mass and it has a volume, so that is a material, right? And take a piece of rubber, it has a mass and it has a particular volume, then it is a material, right? So you are a material because you have a mass and you have a volume, so that is a material. So that is called material, right? Material. Then what is technology? You know about this. Application of scientific knowledge for practical purposes, right? Especially in industry. So what you are going to do is you are going to apply scientific knowledge for practical purposes. It should be, you have to use it in industry for practical purposes. Then you call it technology. So if you are going to use materials in technology, then you call it materials technology, right? Okay, materials. So I am going to divide these materials into two for the moment. Traditional materials. Traditional. So these materials people use, people have been using, and people use this. So they call it, you call it traditional, and you can have high technological materials. High technological materials, especially I am going to aim in this structural material. So I'm going to discuss what are these things. So you can have old materials, so, and you can see new materials, but same materials, but you are going to use it in high technological applications. Well, now structural materials. You know that with the civilization of mankind, that means now people want to do something and they are not in the forests. So they want to use some materials in structural applications. A very good example is metals, right? Metals. Metals emerge as the structural material. Metals. But we know that sometimes we cannot use these metals, for example, say iron, because of the corrosion, right? Corrosion, and maybe it's very difficult to find, you know, that we don't have metal deposits in Sri Lanka. And sometimes you cannot use all these metals in all these applications, right? Because they have different properties. And people look for good materials, for example, nickel-based superalloys. Well, sometimes you have to use it in engines, rocket engines, aeroplane engines, right? Then people use nickel-based superalloys, right? So But we have problems with corrosion is there at high temperatures, right? At high temperatures, corrosion, we call it hot corrosion. So we have problems with even with these nickel-based superalloys. And we can have chromium-based superalloys, but strength is low. Strength is low. Well, now we can think about ceramics. Well, please remember that our main aim was to start with these ceramics in this material. There is a reason for that. We can discuss about it later. So why don't we use ceramic? So what is the definition of ceramic? Ceramic is a non-metallic material, right? It is not a metallic material. Non-metallic, inorganic, so it is not an organic material. You know organic materials, right? It is not, if it is not organic material, and if it is not a metallic material, non-metallic, inorganic, and the required properties obtained by heating. So take a small amount of clay, matty, you know clay, it is non-metallic and inorganic, and if you heat it, then what will happen? You can have a hard material. So you call it ceramic. Not only, I mean, clays, now we have large number of ceramic materials. So non-metallic, inorganic, and the required property, if the required property is obtained by firing, you call it ceramic. So people wanted to use these ceramic materials in structural applications. The reason is availability. So you can find ceramic materials in most of the areas, especially in Sri Lanka, right? Okay, now actually these products are from ceramics. You can see that it looks like metal. It looks like metal, right? Now you can see you can replace metals by ceramics, right? So why ceramics? Why do you go for ceramics? It has a corrosion resistance. You know that if it is a ceramic material, corrosion is not there. You know that these cups and plates and commodes and all these things, so you don't see corrosion there, no? That is very, very, very good property, corrosion resistance. Density is low. You know that if you take, say, iron, density is more than 7,000. That is in kilograms per meter cube. But ceramics, density is, yes, it's maybe 2,500 or 3,000. Density is low. So that is very good when you are thinking about aeroplanes, rockets, and inside engines. If you have a low density material, that is very good. And refractory properties. What are refractory properties? We can work using this material at high temperatures, right? You can use it in high temperature applications, nothing will happen. So that is called refractory properties, withstand to high temperature. And availability. You don't need to worry about ceramics. Everywhere you find ceramics, silica, clay, you know that feldspar, dolomite, silicon and silicon nitride. You know silicon is everywhere. Nitrogen is everywhere. So if you combine silicon and nitrogen, you can produce a ceramic material called silicon nitride, high technological material. And cost is low. Therefore, you know that the cost, because it is available now. So therefore, people wanted to think about ceramic materials, right? So we can have traditional ceramics. You know about ceramics. So if you talk about ceramics, always we remember these, you know, these clay pots and cups and saucers and commodes and all these things. But now we have new structural ceramics, right? So here, what we have to do is we have to produce the material by looking at the microstructure. What is going on inside the material? You can develop materials, right? So these materials are developed materials, and if you can develop these materials, you can use it in many high temperature structural applications inside rockets, inside trains and planes, and in many applications, right? So we can think about these new structural ceramics. Well, you know what is this? It's our Jetavana Stupa. You know that. I'm going to starting from these traditional materials. Kindly, I just want to know, can you hear me?
Yes, sir.
Oh, very good. Yes. So, you know that this is the largest brick building, old one, right? Ancient, biggest brick building in the world, right? This is the biggest brick building, but ancient one in the world. You have seen this, right? You have seen this. And you see that if you are going to learn about this, there you have history, archaeology, chemistry, mathematics is there, right? How the, I mean, how well, we'll discuss it, right? Within a short period of time. And biology is there, physics, technology, engineering, agriculture, etc., etc., etc. Right? So we can do a lot, even using, I mean, now we are in Anuradhapura. So for example, this stupa was there for more than 1700 years, right? So you people do these type of experiments, modulus of rupture of these bricks, because why? How can these bricks there for a period of, I mean, 1700 years? And critical stress intensity factor. These are very scientific. You know that if you measure it, it's very high. And compressive strength, that's why it has been there for a long time. And material removing rate, so many physical parameters, right? So if you see the stress distribution, how the forces applying on this stupa, right? And if you are going to learn about it, then you have mathematics, engineering, physics, art, everything is there, right? Actually, we did it. We did it, and there were some people from some other countries, they came here and they learned about this traditional materials, right? Now, what about Abhayagiri? Yes, that it is also there for a period of long time. Anyway, now these are two historical examples. Now we are in Mihintale, right? We are in Mihintale. Yes, right. Now, if you go in this direction, this is Pulmude. There is a very important deposit in Pulmude. You have a very nice mineral deposit. There you have zircon sand, ilmenite sand, and you have some other deposits also. Zircon, ilmenite, rutile is there, right? Very high technological materials, but you have to treat this. You have to convert this into some. For example, if you can convert zircon sand into zirconia, right? It's like a gem, but we don't do it. We have been not doing anything with, but we have started some work on this. So that is a very high technological material. And if you go in this direction, Epavala, you know, apatite deposit is there, right? Apatite, you know, it's a very good for the plants, and sometimes you can find some apatite where its chemical composition is very similar to the chemical composition of bones. And if you go in this direction near Mahatale, you can have a very high quality silica. And you can have feldspar. There you have feldspar also, right? And if you go little more here, Kandy in this area, in Galaha, you can find very high quality silica. The purity is 99.8% pure silica. So what we do is simply we sell it to Japan, right? Or what we do is we simply crush it and we sell it, right? So we can think about what can we do using these raw materials, right? So one thing is, if you can increase the solubility of this apatite and conversion, so then you can have, I mean, you can give a value for these materials, right? And pure quartz in this area. So you know that it is silica, these transistors, diodes, ICs. So to produce that, you need silicon. Right. Now, strong engineering ceramic. Now we move into the ceramic area. So what are the properties that you need to have high technological engineering ceramic? It should be a high specific modulus materials. Well, high specific modulus means, well, you know the strength, and if you divide it by the density, strength divided by density is called high specific modulus. You can have a high specific, say, Young's modulus, but you have to divide. If the density is low, if you divide it by low number, then the value goes up. For that, strong bonding is important. For example, covalent bonding, right? Now we are going to discuss in our lecture series about these things: strong bonding, covalent bonding. And if you have covalent bonded material, then you have a high melting or high decomposition temperature, right? So it has very good properties, right? Aluminium nitride, alumina, beryllium oxide or beryllia, carbon viscous, silicon carbide. So they are among the high specific modulus materials, and silicon nitride, actually it is normally fabricated artificially, or Cylon. So that is another material that is simply the silicon nitride. If you remove one silicon by one aluminium and nitrogen by oxygen, silicon, then you have aluminum. You can incorporate aluminium here, and you can incorporate oxygen here. Then you call it Cylon. Very high technological and very expensive materials, right? So these are, and that is possible using high technological methods. We can fabricate these high technological materials, right? So as I mentioned, these things are among the high specific modulus materials, but they have problems. These things have problems. These are the problems. Aluminium nitride, easily hydrolyzed. Alumina, thermal shock resistance is low. That means, you know, that if you heat it and cool it, then it cannot withstand, right? It cannot, I mean, then there are problems. Beryllia has toxicity hazard, and carbon has oxidation problems. Then silicon nitride or silicon is the best, right? Silicon nitride. Now, silicon nitride, you know, silicon is everywhere, nitrogen is everywhere, right? If you can produce silicon nitride, it has high strength, very high strength, most of the time better than metals. And wear resistance. Wear resistance means when you use it inside the machine, material won't remove, right? Given wear resistance and high decomposition temperature. right? You can heat it to very high temperatures, maybe 2000 Celsius. But if you use normal iron, you know that it melts. And oxidation, no oxidation, very low oxidation. You know that if you use metal, oxidation is a problem. But if you use this silicon nitride ceramic material, then it has oxidation resistance, very good material, and resistance to corrosive environment. Even in corrosive environments, if you have acids, right? Even in this atmosphere, you can use silicon nitride. So they have very good applications, right? Now, fabrication of silicon nitride, yes, you can powder it and you can use some additives and you apply high pressure during firing, right? But now these are the material things, right? Material science. But you know that simply you cannot heat it and produce. You have to add something. When you add something, it is inside the material and it degrades the properties of the material. So we have to do it very carefully. For example, by looking through the microscope, right? While fabricating, you have to see the microstructure and you have to do some tests and you have to find what is going on inside the material, right? For example, so this is a method for isostatic pressing. That is a fabrication technique, not in Sri Lanka for the moment, right? But we can do all these things. While fabricating, you apply pressure in all directions for the material. If you have, say, complex shape, for example, turbine blade, what you do is while fabricating the material, you apply pressure in all directions. That is called hot isostatic pressing. If you use this method, you can minimize the sintering additives and you can have complex shapes and you can have very improved material properties. And now it involves a lot of science. So you have to think about what is silicon nitride, then you can have silica. This is an additive, right? So simply you cannot melt silicon nitride, you have to add something, right? So then you have to learn about this behavioral diagram. So don't worry about this too much. So it involves a lot of science, right? Scientists, okay, technologists can these things. Don't worry about this too much. It involves a lot of, I mean, it's not traditional. It's not like fabricating plates or commodes or pots, right? Now we have to think about very advanced materials. Japanese people, Korean people, US people, and European people, they do it and they sell it. Actually, we cannot buy all these things. Can you buy a car which has large number of ceramic components? No, it's very expensive. But we have the raw materials, we have the knowledge. Now we have some equipment to test all these things, so we can do, right? Now, don't worry about these things. It involves a lot of science. If you see the microstructure, now this is inside the silicon nitride material. Now, after applying forces, right, you see that this is about 50 nanometers. This is about 50 nanometers. Using our microscopes, actually, we can see the inside of the material. These are some cavities. You can see these things, what is going on inside the material, right? So you see that you can see these materials, right? And don't worry about this too much. What type of cavities are there? Cavities means when you apply, when you are using it breaks. If you know how it breaks, then you can develop the material. This is such an investigation. Actually, we did it. I just want to show you microstructural studies we carried out, and we can give some how can I say methods, how it happens. We can have models to show. This involves a lot of science, right? Don't worry too much about this, right? And what is inside the material. Right now, you can see some impurities inside the materials. And you can use X-ray investigations. Actually, this is in a transmission electron microscope. Then you can identify what is this, what is inside the material. So it involves a lot of science. And oxidation, what will happen when it is exposed to environment? You can, this actually very high magnified, I mean, micrographs. So yeah, by looking at, so you can minimize these oxidation problems and all these things. Right now, right. Not only that, now we are in this area, it's very hot. You know, this, I just want to give a flavor of this structural or material science. Right now we are in this region, very hot. Can we have something, I mean, can we produce advanced material in this hot region? I mean, how to use this? It is a lot of energy. Hot means energy. Now we are facing energy problem, no? Sunlight is a lot of energy, right? So you can analyze the sunlight, and you know that for next 50 years, energy is going to be the biggest problem. Energy. And in 2050, estimated total power consumption is 30 trillion watt. 1 trillion watt means 5 million barrels per year. 5 million barrels per year. So we have to think about energy is there. And well, solar energy, we can think about solar energy is the largest no carbon based energy source, but it should be low cost enough to compete with other resources, not simply normal solar cells. We can think about new type of materials, right? You know that it's not that easy to buy solar panels, but we can think about some other methods. For example, this is called dye-sensitized solar cell. It's another type of solar cell. Cost is low, clean and green technology, and it's very beautiful. You know, you can have different colors, right? We have to think about, and it absorbs photon at different wavelengths. Even you can have it in windows, right? It absorbs most of the photons and does not need high technology, right? And you don't need to find roofs. So even so vertical integration is there. It is possible. This is, I just don't worry about too much. So it involves some science, but not big science. This is simply what is going on. So there you have dyes and these materials. So we know what is going on inside this material. So very simple methods to fabricate these solar cells. It's called dye-sensitized solar cells, right? And okay, and we have some collaborations with some universities. For example, universities in Sweden, Chalmers University of Sweden. Actually, we have collaborative work. They are coming here. Actually, during last 2 years, it did not happen because of this pandemic situation. And Gothenburg University, we have very good collaboration. So they are very happy to even during last few days, we are talking about how to develop these materials. Part of the work we can do here, and we can send the samples there. That is possible. So this is once they, that they visited our university, and we have very good collaboration with Korean universities, Wusong University, and so their vice chancellor and deans are there. So they are very happy to help us, and very advanced laboratories. That's how we design these laboratories. We saw these laboratories and we wanted to have similar laboratories. Now they are very happy about, because they can come here and they can work here, and you can go there and you can work there. This is another university, Chungnam National University. So we have some MOUs with them, and this is Jeju University in Korea, and this is very prominent scientists. So you can see a microscope. So actually we both similar microscope now. So we can actually, we had to go there to do all this work. And yes, lot of, okay. I just want to give you something, I mean, a little about material technology. Well, so now we can start our lecture. Hello, I think you can hear me. Do you hear me?
Yes, sir.
Very good. Now, well, now I am going to start this fundamentals of solid state physics lecture series. Okay. Right. This is MTT 2201 fundamentals of solid state physics. So you can see that the second number, so that is the credit rating. 2 means 2 credits, 30 hours of lectures. Well, I am going to be your teacher. I'm Ananda, and 2 credits, 30 lecture hours. Well, you should know how do you evaluate. We can have continuous assessments, maybe quizzes, mid-semester examination if possible. So you can earn about 40 marks, and in semester 60%. Well, we can discuss about this. If you like this, then we can continue, right? So you can get pass marks from before the examination. If you are very good, then later you can sit for the final examination. Right. Now, you can, if you like, you can read these books actually. So C. Kittle, Charles Kittle, the book's name is Introduction to Solid State Physics, and Blakemore, Solid State Physics, Decker, Solid State Physics, Thomson and Weir, Physics of Solids. Yes. I can send this, right? I can send this, because I have to think about what are the essential things that you need. අපි බලමු හොඳ ඕනම ටික ඔයාලට මේ මොකක්ද කියලා මම ඔයාලට එවන්නම්. මම එහෙම නැත්නම් මම මේක රෙකෝඩ් කරපු කෙවන්නම්, right? Is it okay? Hello? මෙතින්දී දැන් ඔයා සිංහලෙන් අපිට මම සිංහලෙන් කියන මෙතින්දී හොඳට අහගන්න. නැත්නම් ඔයගොල්ලෝ ලියලා ඉන්න එක විතරක් කරයි. ඕනේ වැදගත් මේවා ටික ලියා ගන්න. So if they are very important, you can write down something. But best thing is to learn, right? Try to learn something here. I try my best to explain this very simply, right? Now, you know, televisions, radios, mobile phones, computers, these are new things, no? So inside all these equipment, you have wires, no? Wire, you know. So wire means it is made of, copper, aluminium, maybe sometimes maybe gold, right? So they are called conductors. So wires, copper, aluminum, all these things are called conductors, Sannayaka. And inside these things, you have resistors, capacitors, right? They are insulators. They don't conduct electricity, right? You don't have, you cannot pass electricity. Electrons cannot move. It's very difficult to move electrons inside these materials. And you have diodes, transistors, and all this made of germanium or silicon. So they are in between these conductors and insulators. In between, they are called semiconductors. They are known as semiconductors. So how can one material conduct electricity and the other it cannot conduct electricity, and some of the other materials in between these two? Right. In order to understand these different properties, we must understand the structure inside the materials, how it forms. You know that all of these materials are made of electrons, protons, neutrons, and some other particles. No, these are the major constituents. No, electrons, protons, and neutrons. No, but you know that because of the structure of the material, it gives different properties. If you know the structure, you can change the structure. You know that this is very interesting. We are not simply looking at materials, but we try to change materials. We can have a conducting materials and you can make it non-conducting. And you can have a non-conducting materials and you can make it as a conductor, right? So that is our duty as a material science students, right? Technologists, right? And you are technology students now, you have to do something, right? That's what the developed country people, they do, and they sell it to us, right? But we can do this. You know, this is the first time we are going to have materials technology department in Sri Lanka in the technology field, right? So then the structural arrangements can be related to the different properties. So if you know what is inside the materials, actually, please remember, we can see we can check the structure of the inside the material in our laboratories now. We can do some investigations and you can fabricate very nice materials, because in Sri Lanka you have most of the raw materials, right? Everywhere. You know, in some other countries, they don't have these raw materials. What we do is we simply sell it to other countries. But in our country, you know that if you know alumina, Al2O3, like it's simply, you know that it's a crystalline structure. If you insert small amount of another element, you can fabricate artificial gems. You can make it red color, you can make it blue color, by simply adding small amount of some other materials. So, but we know that we don't do anything here. So please think about it. If you learn this, right? Not only to sit for the examination, eagerly, right? You know that to produce something, the curiosity must be there. Right? So you have very good laboratories and you have very good opportunities, and you are learning physics, chemistry, and all these things. So try to do something, right? So materials technology is the best place for that. We can do a lot here, right? In general, you know, most solids are crystalline. Crystalline, I'll talk about what is crystalline. That's why we are going to learn about crystals, quartz, silica, valley or Kiramanagal, this silica sand is there and silica stones are there. They are crystalline, crystals, like, salt, sodium chloride, you call it crystal. So we will be learning about what is crystal, right? Diamond, diamond, that it is a crystal, but that it is made of carbon, but that you can see another type of carbon also. Both are carbon. What is the difference? How can, how can you change if possible, right? Carbon in different, carbon gives different properties. If you know if you know the structure of the materials, you can do a lot. And ruby, as I told you, this is a gem, right? Alumina, Al2O3, but you have to add something, right? Right. Now, atoms in crystals, right? Now I told you, so they are crystals, no? So these things are crystals. Atoms in crystals are arranged in regular periodic fashion. They repeat themselves in periodic. So, well, what I can do is I'll try to draw something here. Regular pattern mean, sorry. This is called regular pattern. No? It is regular, no? You see that there is a pattern. If it is a crystal, then there is a pattern. So if the atoms are in this way, then you call it a crystal. But if you have atoms in this way, there is no proper order. If the atoms inside the material is like this, then you don't call it a crystal. So this is a crystal and this is not a crystal. So regular periodic fashion. Periodic, that avartiya. There is a pattern. When you go there, then you can see so there is a pattern. If you go there, it looks like the same. And if you go here, it looks like the same. Just a moment. Nami. Oh. Huh? Makada? Okay, I'm going to right? So, well, you see that if you arrange the atoms in a special way, so you can have a crystal. But if the pattern is not there, then it is not a crystal. People call it amorphous, right? So that is the difference, right? And in nature, matter exists in three main status, right? Normally, you know that in matter exists in or maybe it is in the form of gas or liquid or solid. Vayuva, dravya, ganya, right? Gases, liquids or solids. So what is the difference? You know that water exists like a gas, steam, and sometimes it appears as liquid, water. Then if you then you have this material in another form, ice. If you know what is going on inside the material, then you can think about other material also, right? So what are the differences between these same material in the gaseous stage, liquid stage, and solid state? So these different states are determined by the strength of interatomic or molecular attraction. Now, Now suppose this is one atom and there is another atom, right? So these different status are determined by the strength of interatom. There is a bond between these two, right? There is a force between these two atoms, right? So I cannot draw. I mean, suppose these are right something like spheres. Same thing, right? So you have to think about the force between these two, right? And type of bonding. What is the reason for having this force between these two? Maybe this is positive, this is negative, or maybe they are sharing electrons. This is also sharing electrons with this. Maybe you don't have any connection with these two. Then you call it a gas, right? Right. So these different states are determined by the strength of interatomic or molecular attraction. This may be an atom, right? This may be an atom, or this may be a molecule. You can have molecules and atoms also, right? Right now, is this right? Now gases. The constituents are in constant motion and collisions between atoms are infrequent. Now, if it is a gas, these molecules are moving here and there, right? And there are collisions, right? And do not occupy in a fixed position, right? So they don't stay in a particular position, right? They move here and there. That is the property of gas, right? Gas atoms do not occupy in fixed. It won't stay here. It moves here and there, right? And at the same time, they collide with some other molecules also. The intermolecular attraction is so weak. The attraction between two molecules, it is very weak. It is not strong. And the molecules move independent to each other. They don't worry about the other molecules, right? They can meet these other molecules and they hit with these molecules and it moves away. There are no bonds between these if it is a gas. And the average atomic separation, that means distance between two atoms at standard temperature and pressure. Sammata Ushnataya Pidana, you know, standard temperature and pressure, it's about 2 to 3 angstroms. You know what is angstrom? It is 1 angstrom is 10 to the power, sorry, not 10 to the power minus 10 meters, right? Sorry, this, you know, 10 to the power minus 10 meters. That means you divide meter by this number 1 and 10 zeros. It's a very small. Actually, this letter is Swedish A. You know, this is not normal A. You put a small circle here. That is true. I mean, that is for that scientist. His name is Ångström. His name is Ångström, not Angstrom. No, the people, I mean, in Sweden, they call it Ångström. That is the correct pronunciation, Ångström, right? Ångström means 10 to the power minus 10 meters. Right, so the average atomic separation at STP is 2 to 3 angstroms for gases, and the average number of atoms or molecules 10 to the power 19 per milliliter. You know what is milliliter, right? Milliliter means 1 centimeter, 1 centimeter, 1 centimeter size. 1 centimeter, please you think about, and you can use your fingers to have, I mean, 1 centimeter in one direction, 1 centimeter, 1 centimeter. So that size is called milliliter. There you have 10 to the power 19 atoms or molecules. in gases, right? And liquids, now what you do is you apply a pressure to gas. You apply a pressure. You know that now these days gas problem is there, no? You have this gas, LP gas. So what you do is you apply a very big pressure, then it becomes a liquid. So that's why you have this LP gas as a liquid inside the cylinder. You apply a high pressure, then it becomes a liquid. Right? If pressure on gas increases, the atomic separation reduces to a few angstroms, and liquefaction is there, right? And please remember, when you write angstrom, right? This is the way that you write. Don't put capital A here, right? That is wrong. If you put capital A here, that means we are talking about Mr. Angstrom. Mr. Angstrom is going to Colombo. Then you write capital A and that dot if you want. Even if you write here few newtons or whatever it is, the n should be simple, right? So when you use it as a unit, you start with a simple letter. So few angstrom units, right? So if you apply a pressure, then atom come very close to each other. Then the concentration is 10 to the power 22 to 10 to the power 23 per milliliter, right? So previously it was 10 to the power 19, 10 to the power 19 atoms or molecules per milliliter. Now it's 10,000 more, 10,000 close. It's 10 to the power 22, 10 to the power 23 in liquids, right? In solids, atomic separation is of the order of the nearly 5 angstroms. And the attraction between molecules is very high to hold the molecules in fixed positions. Now you cannot move them. It's not that easy. In solids, right? Atomic separation is, it's nearly the same, but molecules are in fixed positions. And the concentration is 10 to the power 22, 10 to the power 23. Previously, for liquids, it was the same. No, for liquids, it was the same, right? 10 to the power 22, but same as liquids, but the attractive forces are stronger than that of liquids. So the forces between the molecules, so atoms, are now very high. Then you have a solid. You see that, right? If you can break this force, or if you can break this bond, it becomes a liquid, right? In solids, the atoms or molecules cannot move freely but vibrate around fixed positions, right? That means in solids, if suppose if this is a molecule and this is also a molecule, right, or atom, then they vibrate in this, they vibrate, right? Vibration, that movement is there, right? Cannot move, but they cannot move freely. They cannot move freely, but they can stay there, but they can move here and there. They can vibrate. Actually, when you heat it, what happens is the vibration is very high then. When you heat it, the vibration is very high. When it is cool, the vibration is small. Not that small, right? It's a very high vibration, but vibration is low, right? So in solids, the atoms or molecules cannot move freely, but vibrate around fixed positions. They vibrate. They cannot move freely. Right. Now, solid state. So now we are talking about fundamentals of, that is the topic, no? That is the course, fundamentals of solid state physics. Solid state, we are talking about solids. The atoms or molecules in solids can be stacked in random or ordered manner. What is that? as I told you, yes, I explained it a little while ago. So you can have a ordered manner. That means there is an order. There is an order, right? And you can have atoms in, right now there is no order, right? There is no order. You call this a crystalline solid, and you call this an amorphous solid. So there are two types then. Crystalline, there is a order and there is a periodic manner of, staying in this position. But here there is no periodic large number of molecules. Right? You have to draw large number of molecules. Then you call it amorphous, right? Crystalline and amorphous. Right. Now, if you consider a small region, now I don't see this. Right. Now consider a small region. What happens? Yes, sorry. Now consider this small region. Now in this region, there is a periodic fashion, and in this region, again, you have a periodic fashion, right? And there also you have a periodic fashion. So in this region only, right? So you can have, you consider a small region and few hundred atoms. So we may find these atoms are ordered. Now these atoms are ordered in a regular periodic fashion. Right? In a regular periodic fashion, right? And there also, there is a periodic fashion. And there also you have this periodic fashion in small region, right? Right? If this periodicity is found not only in the small volume, but throughout the solid, if this pattern is, right, not only here, if you have the same pattern in everywhere, right? Then you call it a single crystal. But this is not a single crystal because pattern is in this region and there is another pattern in this region and there is another pattern in this region. But if you find this pattern throughout the solid, mulu solid deka purama, then you call it a single crystal. Single crystal. You know that this Chudamanikya for stupa, that's, it gives very nice colors, and because it is a single crystal, right? Single crystal, we can form single crystals, but, right? So please remember, if this periodicity is everywhere, then you call it a single crystal. But you can see that this is not a single crystal. If, however, in the small volume we find discontinuity in the periodic pattern, now you are right. Okay, now in this region you have periodic pattern, and in this region periodic pattern, in this region there is a periodic pattern, then you call it polycrystalline. So this is a polycrystalline. There you have a pattern, there you have a pattern, there you have a pattern. Polycrystalline. So this is a polycrystalline, right? Right, and this is the locus of discontinuity. මේක තමයි අර මේ හැඩේ නැති පතය. දැන් මේක මේ ටිකේ විතරයි තියෙන්නේ. This is the locus, පතය, locus of the discontinuity, right? This is the locus of the discontinuity, right? Is called grain boundary. This is called grain boundary. මේ තමයි boundary. This is the boundary. This is called grain boundary. This is called the locus of the discontinuity. So these are grain boundaries, right? Grain boundary. Where the periodicity is maintained, right? This region is called grain. This is a grain, this is a grain, and this is a grain. Right there, you have three grains. Right? Periodicity is there, and here you have another periodicity, and here you have another periodicity. This is a grain, this is a grain, and this is also a grain. Right? Is that clear? Now this is a polycrystalline material, and if you have this pattern everywhere, then it is a single crystal, and if it is only in this area and this area and this area, then you call it polycrystalline. And if this grain size is very small, okay, maybe you're right. If it is very small, that means you don't have any periodicity, then you call it amorphous. There is no order. So if this region is very small, that means there is no periodicity. No, there you don't have periodicity, there you don't have periodicity, everywhere you don't have a periodicity. So then you call it amorphous. So you can have now three types: single crystal, periodicity is everywhere, and periodicity is in these regions, then you call it polycrystalline. And if this periodicity is, maintained in a very small region, that means there is no periodicity, then you call it an amorphous then solid. So you can divide the solid mainly into these three categories: single crystal, polycrystalline, and amorphous. Right. Now, whether a solid is polycrystalline or single crystal is determined by how the solid is formed. Now, you know that, you can form this solid, no? You can form maybe ice, water, whatever it is, and maybe you can form some other material. So whether it is a polycrystalline, single crystal, or amorphous is determined by how the solid is formed. Right? For example, usually solids form from rapidly cool. If you cool it very rapidly, now you have a liquid and you cool it very rapidly, right? Then it is an amorphous material. They don't have enough time to go to their positions, right? Right now, they don't have, for example, here, if you have, say, atoms and all these things in a liquid everywhere, right? And if you cool it very rapidly, then they don't have time to go to these places, no? Then atoms or molecules are everywhere, here and there. So if you cool it very rapidly, if you cool the liquid very rapidly, then you can have amorphous materials. And single crystal, that means everywhere you have the same pattern. So single crystal have to be grown very slowly. So if you want to form a single crystal, you have to cool the liquid very slowly. In between, you can have polycrystalline. That's what I told you. You have this very high quality amorphous silica in Sri Lanka. And if you heat it and if you melt it and if you cool it very slowly, you can form a single crystal. Manikap wage, you know that it's like a gem, right? It gives nice colors. If you cool it very slowly, you can form a single crystal. That's why it gives nice colors and reflections and all these things are very in. But if it is, if you cool it very rapidly, then you can have this normal glass. You know that window glasses and all these things. How do they produce? Rapidly cooling. That's why strength is not that much. Strength is very weak, no? If it is amorphous material, strength is very weak. What you have to do is you have to cool it very slowly, and in between you can have polycrystalline, right? So, right now, single crystal alumina, right? Single crystal alumina, if you take aluminium oxide, you have aluminum +3 and oxygen -2, right? Now you have a regular array of aluminum and oxygen ions held together by electrostatic forces. You can have aluminum in one place, right? Sorry, aluminum. Here you can have aluminum. Right, and you can have, it's not exactly the way, I mean, I just want to show you. Yes, what happens? Okay. And oxygen may be somewhere here, right? Throughout the crystal, this is the pattern. Here you have aluminium and here you have oxygen, right? Regular array of aluminium and oxygen here ions held together by electrostatic forces, because you know that this is positively charged. Aluminium is positively charged and this is negatively charged. There you have a electrostatic force, Vidyut Akarshana, plus and minus, right? So, well, this is not the exact way. I just want to tell you that if it is everywhere, if it is throughout the crystal, then that is single crystal alumina. So there are bonds between aluminium and oxygen, right? But if you have the same material, you cannot have plus and minus, no? Then there are another type of bondings. Bendima Venus. They are sharing electrons, maybe. Right. Okay. Now you see that this involves lot of, not lot of, I mean very simple science. Right. If less than 1% of aluminium is replaced by chromium, right? If less than 1% of aluminium in this aluminium and oxygen, chromium, we form ruby, manica, artificial gems. So if you can replace 1% of aluminium by chromium, then you can have ruby. And if we replace this by titanium, then you have sapphire. You have heard about these gems, right? So that is called sapphire gem. And perfect single crystals are rarely found in nature, right? That's why you cannot find everywhere very good gems, because the formation was in different manner, right? Not very slow cooling or slow heating, or that's why it is very difficult to find perfect single crystals on the earth. So that's why it's very expensive. In some places, in Ratnapura area, maybe in some other places. So what we can do is maybe we can try some single crystals inside the laboratories, right? So because we can control the environment, right? Now crystal structures. Crystal structures are right. Okay, now it takes some time. Sorry. Pen. Right now, you know that they are in a periodic manner. Right. Now, okay, this goes to infinity, right? This also goes to infinity. I cannot draw. And this is a two-dimensional, right? I just draw some dots, right? These are some dots. And actually they are places. They are places. Right? They are not atoms now, right? Some places. Every crystal can be classified according to the shape of its space lattice. Now I told you this is a crystal. We call it a crystal. If you have a ordered manner, please remember that now this is a two-dimensional. Actually, in the perpendicular direction, you can draw. You can put some dots there also. This is a two-dimensional one. I cannot draw 3D here, right? To reproduce the crystal, we specify a set of points. Now to produce the crystal, we specify set of points in space such that the arrangement of points about any given point is identical with the right. Now you have these points everywhere to infinity. There you have infinity. There you have go to infinity and infinity, and perpendicular to this plane in my direction and in the opposite direction, you can have large number of points, right? A set of points, right? Now, if it goes to infinity, no, ananta yanakan thiyena. And if ananta yana, if you go here and if you have a look around, it looks like the same, no? Because it goes to infinity. If you go and sit here and if you look around, it looks like the same everywhere. And if you go to another point and if you look around, then it looks like the same. And if you go to another point and if you look around, it looks like the same. Do you understand? That's what I have written here. Every crystal can be classified according to the shape of its space. That is, to reproduce the crystal, we specify a set of points in space such that the arrangement of points about any given point is identical with the arrangement of points about any other point. But don't worry about this shape, right? You can have, later we will discuss this, you can have right, this shape also, no, not right, this is also regular pattern. Don't worry about the distance between atoms. You can see that in one direction it's small, and in one and now this is another type. Right? So not only this one, right? But also this one also. Maybe the distance between these two and these two are not the same. Right? So don't worry about a particular shape, right? It's not this shape, maybe in some other direction, or maybe distances are not the same, right? So, but if you go to this place, but this goes to infinity, this goes to infinity, this ananta yanava, and if you go to any point and if you look around, if it looks like the same, then This set of points is called a space lattice, right? You go there and have a look around. Okay, now everywhere it's the same. If you go here, everywhere it is the same. But and if you go here, you look around and you go there and have a look because it goes to infinity. If it looks like the same everywhere, but there is a pattern, no? Then you call this set of points, no atoms, right? Please remember now these are simply places, points, Lakshya, no atoms. So then you call this a space lattice. This is a space lattice, right? That is called a space lattice. In Sinhala, you call it Dali Savakashe. Now it is not in Sinhala medium, no. And it is the space lattice is better than Dali Savakashe, no. There you don't understand anything. So right now we are going to form a crystal. For that you need this space lattice, right? This is the space lattice. Space lattice, right? Okay, now in two-dimensional, right now this is two-dimensional, no? Two-dimensional means this is y direction and this is x direction. Only two direction. This is also 2D, no? This may be your y, this may be x. 3D can, you know that three-dimensional, you know about it. Right? This is 2D. In 2D, it is only possible to form 5 different space lattices. That is important. In 2D, you can form only 5 different space lattices. In 3D, only 14. Right? In 2D, you can form only 5 different space lattices. In 3D, you can form only 14. If you want to read more about this, please read this book, Kittle. So I gave you this as a reference, Charles Kittle book. At the beginning, I mentioned about books to read. Charles Kittle, it's a very good book. And you can download it if you want, Kittle book, right? So it's good to read more about this, right? A space lattice is a set of points, not a set of atoms, right? There you don't have atoms. These are simply points, And to build an ideal crystal, we take a space lattice and at each lattice point, we place a cluster of atoms, right? So now if you want to have this crystal, right? Now what is this? This is a space lattice. Now if you want to have a crystal, what you do is you can have I don't see. You can have maybe molecules, so atoms. Not only atoms, right? You can have molecules, right? There you put molecules, maybe oxygen. Maybe here you can have oxygen. Here aluminium, oxygen, aluminium, or maybe you can have a molecule here. It consists of 2 or more molecules, and there also you put a molecule. Then you call this a crystal, right? If you place molecules in these lattice points, space lattice, then you call it a crystal, right? Without atoms or molecules, it is a space lattice, and if you put atoms or molecules, then you call it a crystal. And the set of this molecule or the atom is called basis. That is called basis, right? If you put molecule or atom here, then that is called. So that means space lattice plus basis is the crystal. So basis may be one atom or several atoms. Right. So 2D rectangular lattice plus basis is a crystal structure. So 3D rectangular lattice plus basis. Basis means everywhere you have to put the atom or molecule. Then it is oh sorry. This is please. I am not going to correct it here. CRY, right? Crystal structure. So the choice of lattice point is not unique, but the shape is unique. That is also important, right? So I told you that there are 5 different space lattices in 2D, no? So this one, don't think that this is one space lattice. Okay, now this is one space lattice, right? This is one space lattice. How about this one? It is the same shape, right? And this distance, same shape. This distance is equal to this distance, and same shape. This distance is equal to this distance, but this distance is not equal to this one. That does not mean there are 2 types of space lattices. It is the same, right? It is the same. So the choice of lattice point is not unique, but the shape is unique. Shape again tamai nama den. We will be talking about this later. Api මේකට නමක් දෙමු sir. Okay, so if you call it simple cubic, this is also simple cubic, right? Because don't worry about the magnitude of this. This may be say 1 centimeter, 1 centimeter. This may be 2 centimeters, 2 centimeters. But the space lattice is the same. It is the same, right? But if you have a different style, you can have a different styles. Later we will talk about this. Then you, if you have a different style, suppose that this is one structure. And at the center also, there is another point. Okay, now it is not the same, right? That is another space lattice. This is another. This is one and this is another one, but this one and this one is the same. If the shape is the same, it's the same space lattice, right? Same lattice, but this one and this one, they are different. Right. Right. Now, fundamental translational vectors. Fundamental translational vectors. Right. Now I have to draw something here. right? Now, sorry, actually, I had no time to draw all these things. Next time I'll do it. This is O and this is A. And this is B. And this is simple A, right? If I draw it. And this is simple B. Right? Fundamental translational vectors. Then now inside the material, now we are going to talk about vectors, bicycle. You know, vector means it has a magnitude and direction. This A and B are called fundamental translational vectors, right? Now, this I'll call this I. Now this is a vector. Now if you want to go from A to B, then you have to go in this direction and you have to go in this direction. Now in this case, actually this should be 2, no? Right, if you have to go from A to B, you have to go 2A in that direction because this is A, this is A, so this is 2A, and you have to go 2 in that direction, that is 2B. 2A plus 2B is equal to I. And that is called crystal translation vector, right? A vector connecting any two lattice points of a space lattice. Now, if a vector connecting any 2 points in space, right? Or in 2 lattice points, this is called crystal translation vector. It's very simple, right? It has a direction, and it has a magnitude. Therefore, it is a vector. So, vector connecting any 2 points, any 2 lattice points is called crystal translation vector. And the small ones, that is the smallest in that direction, no? Maybe this is longer than this one. These A and B are called fundamental translation vectors, right? So this is fundamental translation vector, and this I is crystal translation vector. Right? Now, I can name this as R, and I can name this as, sorry, it's not that good. Oh, how can I go back? Sorry, it has gone. You know how to get it back? No, don't worry about it, right? So this I is called 2A plus 3B. This is a translation vector. Right. Now, that R days I have drawn, I'll redraw this and I'll send it to you. R plus I. So given in, now it was a 2-dimensional one, no? And in 3D, you can have three fundamental translation translation. This should be translation vector, right? In 3D, this is translation, right? Translation vectors given in 3D. In 2D, you have A and B. In 3D, you can have A, B, and C. And these vectors are such that the atomic arrangement looks the same when viewed from R and just for, as I told you, right? At any point, it looks like the same, right? So these, don't worry about these too much. So A, B, C are called fundamental translational vectors, and this N1 and N2, N3 are called integers. I told you that R is equal to 2A plus 2B, no? This R is equal to, not R, no, I is equal to 2A plus 2B, right? These are fundamental translational vectors, and these are integers. Integers means you have this plus or minus, right? This may be plus, this may be minus, then it is, and they are whole numbers, not I mean half or 1/3. So this R is, if you can write it in this way. In 3D, you can write another one, plus 3C or whatever it is. So these are fundamental translational vectors, and these are integers, Nikila. Right. Now, consider two-dimensional square lattice. Now, this is a square lattice, right? Square lattice. These are points. These are points, right? And now here you have A1 and A2. So this is A1, this fundamental translational vector is A1, this is A2, right? And here you see that this is A1 dash, and you can name this as A2 dash. You see that the shape is not the same, right? Now I take this as A2 dash, and this is this as A1 dash. This is the second one, and you see that now I go two in that direction. Now this is, you see that this one, right? This is called A1 double dash, and this translational vector is A2 double dash. And here you have two squares. This is A1 triple dash, and this is A2 triple dash, right? I just draw these things, right? Don't worry too much about this. Now this is a 2D square lattice. Square means make a square එකක් වගේ. Square වගේ කියන්නේ හරි හතරස්, you know that square, right? There I have this vector and this vector, and you have this vector, and I can go in that direction. And there, yes, this is the same, but this is very long now. But in this case, I go in that direction, that is 2, and here I have 1. So all pair of vectors of each cell, you call this is a cell. You have 4 cells. Shown are translation vectors of the given lattice. So these are translation vectors. But vectors of cell 4 are not primitive. Now this is not a primitive. Why? You have to go to, I mean, now in this case, this is 1, and in that direction, it is also 1 in that direction. But here, 1 in that direction, but 2 in that direction. in the cell. So 4 is not a primitive translation vector. So cell 4 is not a, so these 3 are called primitive cells. How do you identify the primitive cells? Area is the same. You know, area of this one is the same as this area and this area. You know how to find area, A2 multiplied by A1. Here, how can you find the area? A1 dash multiplied by this distance, no? So how do you find the area of this cell? Base times this perpendicular direction, perpendicular line. If you draw a perpendicular line, simply you see that this one plus you can bring this one here, no? This triangle, you can bring this triangle here, then the area is the same, right? So you don't see that any difference in area of these two. Or simply, this is the shortest distance in that direction, this is the shortest direction in that direction, this is the shortest distance in this direction, and this is the shortest distance in that direction. Right here also, this is the shortest distance in this direction, and this is the shortest distance in that direction. If they are the shortest distances, then you call them fundamental translational vectors. But here, this is the shortest distance in this direction, but this is not the shortest distance, because this is the shortest distance in that direction. Then this is not a primitive translational vector, and this is not a primitive cell. This is not a primitive translational vector, and this is not a primitive cell. And this is a primitive cell, primitive cell, primitive cell, non-primitive cell. Primitive translation vector, primitive translation vector, primitive translation vector, primitive translation vector. Primitive translation vector, primitive translation vector, that is the shortest distance and in that direction. And here, shorter primitive, but this is not primitive and this is not primitive. So, cell 4 is not a primitive cell. It's because lattice translation vector can't be formed by, so name is given T here, right? Can't be formed by any integral combination of the corresponding pair of vectors. But for all other cells, the pair of vectors are primitive translation vectors. Cell 1, 2, and 3 each are primitive cells, and they are all equal in area. Cell 4 has twice the area of other 3 cells. So this leads us to define primitive translation vectors, right? So you have primitive ones and non-primitive ones, and primitive cells and non-primitive cells. Right. Now, primitive translation vectors, ABC are primitive translation vectors if the condition given by equation 1 satisfying with n1 integers. So this is the equation 1. Right? R dash is equal to R plus N1A, N2B plus N3C. If these N1, N2, and N3 are integers, ABC are translation vectors if the condition given by equation 1 satisfying with ni integers. In other words, ABC are primitive translation vectors if they represent shortest distance in their direction. Therefore, 4 is not a primitive cell. 1, 2, 3 are primitive sets. Area of 1, 2, 3 are same. They are primitive cells. In general, the simplest is chosen as the primitive cell. Saralava keyword. Simplest one. This is the simplest one in this shape. This is the simplest. You can draw half of this, then what will happen? You have to go in that direction, half of A21, no? So this is the simplest one. This is the simplest one, but this is not the simplest one because you can remove this and you can have this one and you can have this one plus this one gives the big one. So simplest one is the primitive one. Right? So vectors in the lattice. The simplest is chosen as the primitive cell. Right now, in 2D case, simple rectangle. So this is a rectangle, not a square, right? A is greater than B. Right now, the significance of primitive cell is that the primitive cell is the one of smallest volume, which could serve as building blocks of the structure. Then, now you know that now we are going to, now suppose that this is our screen, no? So now this is the, say, crystal. Now what I am going to do is I am going to use this one to fill this one. Here I have one of this one, and I bring this one again here, 2, 3, 4. So I am going to fill this screen with this one, right? Primitive vector is the primitive cell is one of the smallest volume which could serve as a building block. A building block, like it's like bricks, right? So this is called primitive cell. This is simplest one is called primitive cell. Right? For a given space, that is, all possible primitive cells have the same volume, right? As in the previous case. Now in 2D case, area is the same. In 3D case, all the volumes are the same, right? Well, I'll next time I'll explain this again because this is very important. Now we are talking about structural materials and atoms inside the materials and the shape of the structure inside the material. So you should know all these things. For example, if you take, say, diamond, or if you take another material, maybe ruby, or if you take another material, maybe iron, what is inside, how it forms, using which primitive cell. And if you know all these things, we can design materials and we can fabricate materials. So we can go for a very advanced materials. So raw materials are here, equipment are here. Now you are following this course and you can design some materials. Actually, at the beginning, we did not want to give you a very complex things, but later you can design materials, right? You go out and you collect some samples and you can bring it to the laboratory and you can fabricate a very high quality, high level material. So that's the aim of our material technology department, right? So we have the labs, we have very good students, and if you study this very well, you can design materials. Probably by simply slow cooling, maybe heating with the required conditions, and looking through the microscope and applying some pressure on it. And so these are called material technology. You will see that it's really interesting, and actually, unfortunately, I cannot show you. Something is wrong with my computer. I can show you some materials which we developed, not actually in Sri Lanka. It looks like metals, but what we do is we take it from outside, I mean, in some mineral deposits, and we can fabricate very high quality materials. So for the moment, I stop here, and okay, see you next time. Right, okay, bye.
Thank you, sir.
Okay, thank you.
Thank you, sir.
Okay, thanks.